the curves way back when we were talking about Duhamel's principle?
Yeah.
So let me just recap that, because if you were asking about it, maybe other people do have a question about that too. So if you remember when we were working with Duhamel's principle, what we had to do is basically to split up this integral that gave us the value of u at x0, t0 into a line integral, essentially around the three segments of this triangle, right? So this is x0, t0. This is x0 minus c t0, 0. This is x0 plus c t0, 0. Okay. And then we want to come up with parameterizations. I think maybe it sounds like it was clear how you deal with this segment. Let's talk about the second segment, and then the third segment is quite similar. So to get the second segment right, you need to come up with a way to parameterize this line so that this isn't a very good drawing. So that we have just a single parameter that determines where I'm living on this line. Call that parameter S. Okay. So if I'm starting here at x0 plus c t0, 0, and I'm going up to x0 t0, right? I have two choices, right? Or, you know, I actually have an infinite number of choices. But usually what you want to do in this case is you want to just call one variable s, if you can, or some simple manipulation of s. And then the other variable would be some function of s, right? And in this case, because you're going from t equals 0 up to t0, that's a natural variable to just associate with s. So that's why we assign t of s to just be s in that case. And then I need to figure out, basically, when I go from here to here, how is x changing? And it's easier when you have just a line, because the endpoints, you can just check the endpoints and you know everything in between will be fine on just a straight line, right? And so I need a linear function of s that when s is 0, I get this. And when s is t0, I get just x0. Okay. So x of s then, in this case, right, I know that it should be x0 plus some function that when s is t0 is 0, right? So it turns out that, you know, in this case, I know when s is t0, this whole thing should vanish, right? But then when s is 0, I want this to be c times t0, right? And you can get, you know, more, you can get more involved, and you can do like a point slope formula or something like that, right? But here we're just sort of, you know, guessing the right point slope formula. Okay. So that's our x of s there. And then I think the last question you had, maybe the last question I'll answer is about the arc length formula. Is this clear how you get this? Do people want to ask questions about that? Or
Actually, I didn't have a question about this. It was just about the limits, about how we change the limits.
oh, just on L of S on the arc length formula?
Yeah.
Oh yeah. So your arc length formula in general is just going to be L of S. That's, you know, how long that line is with respect to yeah, how long is that line that you're parameterizing along, okay? And so for a given value of s, you start off with some value of s0. But I mean, in general, this is just going to be 0, right? I mean, there's you could have S, start off at some value that's not 0. But here we're taking the simplest case where S0 is 0. So with a thing, when I wrote down S0 here, that's really just 0 here. And then S here is how far you are along. So this is saying, given, as I move along this line, for a given value of S, how long is this line L of S at a particular value of S, okay? And then, to do the chain rule right, you have to differentiate this arc length formula. So how do you differentiate this thing? Well, the arc length formula, again, it follows from like Euler's, or sorry, Euclidean distance, okay? The change in x squared and the change in t squared, some of those, the square root of that. So that if I compute dl ds, right, fundamental theorem of calculus means I just differentiate this and then I just evaluate it at s, right? So then what I get is that this is going to be equal to dt ds quantity squared plus dx ds quantity squared. And what are these things? Well, I can just get them by differentiating these formulas, right? dt ds is equal to 1, and dx ds is equal to c. Minus c. So then this is equal to square root of 1 plus c squared. That's it. Yeah, that's all there is to that arc length formula. Anything else?
What if it was left in variable terms? And if we didn't have an explicit formula for x and t?
Well, you're in trouble if you can't parameterize x and t. I see what you're saying. You may have an implicit formula, in which case, sometimes even if you have an implicit formula for x and t and s, you can find an explicit formula for their derivatives. If you can't do that, then you have to find another way around, or you'll have to do it like numerically or something like that.
Choose a different contour.
But
yeah,
like
but
could
hopefully,
you,
if it's a solvable problem, then you should be able to, parameterize it in a way where you can take these derivatives.
okay, but could you leave it in the variable form, like not substitute dt over ds and dx over ds and then differentiate them, and maybe show a general way of how that formula would look like?
I'm not quite sure what you're asking. You're asking me to be able to perform a line integral, but not have parameterized the line first?
Yeah, suppose you're not able to parameterize it. Can you find dl over ds in that case without knowing dt over ds and dx over ds?
I don't know about that. I think, for this, typically when you compute a line integral, the idea is that you have a one-dimensional contour, and that you need your integral then needs to be along a single dimension. So what you're saying is, what if I just leave things in multiple dimensions? What's going to happen? Well, then, I mean, at the end of the day, whatever you do, you need to bring your coordinates down to a single dimension. So,
And I mean, if you can't find a parameterization, then S doesn't really have any meaning at that point.
yeah, and the parameterization is arbitrary, right? I mean, I could have very well chosen an infinite number of different parameterizations here. That would have worked. And because it's a straight line, I mean, it works out nice in this case. I mean, the difficult cases are like when you have, some weird shaped line or something like that. But yeah. I mean, either way, a line integral needs to be projected to a single dimension. You can't, I mean, you just can't compute the integral that way if you can't project it to a single dimension. So, are you like working on a problem where you can't parameterize a contour or something, or
No, I mean,
you're
it's
just
just that
trying to think of how
taking
to?
taking derivatives of integrals of some variable functions just scares me. So I thought there might be some tricks to solve them.
Yeah, I mean, the good news is here that for the change of variables formula, you really, all you need is this integrand, right? The derivative just removes the shroud of this integral, right? So really the thing that you're computing here is just this, you know, derivative of the arc length. Yeah. So you can jump to this formula at the outset if you like. All right. Okay, so that's those questions that you have. Let's switch gears.